All right, folks, thanks for tuning in on this beautiful Friday morning. This is lecture 23 of Chemistry 132B. And this is the last lecture in which we will be looking at something new, because on Monday next week, we'll be starting to review all the material of the course. So this is really the last part of the course. And today, we will not be introducing a lot of new stuff. I just want to go over something we have already done, but look at it maybe from a slightly different angle to basically dot the I's to make sure that we understand the procedures that we're using here, so that it doesn't appear to be all magic, because sometimes when you see these things for the first time, it looks like, you know, totally hocus pocus. But that's not what it is. This is all, you know, procedures that I think we can understand, and we can even pursue them. We can even actually execute them to find solutions to problems that are of direct interest, I think, to us as chemists. So last time we spent a little bit of time on some simple molecules with pi conjugated systems. This was the simplest version, ethene, and we were trying to solve the Hamiltonian matrix to find the molecular orbitals. That is what we were doing. So today we're going to do the same thing, but I would like to do it explicitly. So I would explicitly like to solve the matrix, the Hamiltonian matrix, and diagonalize that matrix and see how that is done. Okay, and from that procedure, hopefully it will be clear on how you can use the information from the mathematical steps and then apply them to the actual physical problem. So what did we do? Well, we said these are p orbitals from carbon atoms. There are 2 carbon atoms. Each one contributes an electron in a p orbital, and we're going to do or make molecular orbitals from these 2 atomic p orbitals. We know if we have 2 orbitals to start with from each atom, sorry, 1 orbital from each atom, a total of 2, then we can make 2 molecular orbitals. The first one is we can call psi A. Okay, so that's a linear combination of atomic orbital 1 and atomic orbital 2. And then there's also an option B, which is also a linear combination, and it differs only by the values of those coefficients in front of it. Okay, so our job, of course, is to find those coefficients. And the way we've done that is through 2 potential ways. The first one was the variation principle, which explicitly is trying to find coefficients that minimize the energy. Okay, that's one procedure. But the other procedure that we talked about this week is by looking at the Hamiltonian matrix and diagonalize this matrix. That also gives rise to solutions for the energies and solutions for the coefficients. Those are the things that we'd like to find. So here is the Hamiltonian matrix. Once again, it has alphas and betas. And these alphas and betas are part of the Huckel approximation. This is important to understand. So we have made already at this level the Huckel approximation for pi conjugated systems. Just to remind you, these alphas and betas, what are they? Alphas are defined as the diagonal elements of the Hamiltonian matrix, whereby the states 1 and 2 are the atomic states. Okay, the Hamiltonian is not an atomic Hamiltonian. It's a Hamiltonian of the entire system of the 2 atoms. It's the molecular orbital Hamiltonian. But the states between which the Hamiltonian is sandwiched here are the atomic states. So these are not eigenstates of the Hamiltonian. That's important to understand. So we cannot really directly find solutions to these integrals. This is a complicated problem. So we have to find these integrals typically in a numerical way. The beta integrals are quite similar, with the important difference, of course, that the bra and ket are not the same on each end, but are actually different. Okay, these are nearest neighbors. 1 and 2 are nearest neighbors. 1 and 3 would not be nearest neighbors, and those integrals within the Huckel approximation are going to be 0. Okay, so this is all just a set of definitions that we have used to make the problem manageable. So what do we have to do then? Well, we have to diagonalize the matrix, and that's exactly what we did last time. And then from that procedure, we found the energies. They were found on the diagonal. And the energies in this particular case are alpha plus and minus beta. And here is the molecular orbital diagram. Nothing has changed. This is exactly the same compared to what we did last time. Nothing has changed, right? So this is the molecular orbital diagram within this Huckel approximation for the p orbitals. And we find two pi orbitals, a bonding and an anti-bonding, and they're split relatively to one another by a value of 2 beta. So that is the same as we talked about last time. So today what I'd like to do is to look at this Hamiltonian matrix, okay, this guy right here, and see can we actually diagonalize this? How is that done? And what kind of tools can we use to make that work? Okay, this is of course the simplest case. This is a 2 by 2, but we will also be considering maybe more complicated cases where we have a matrix that is much larger than 2 by 2. Okay, so how do we do this? So I'm going to take this Hamiltonian matrix and I'm going to write it slightly differently in the following way. So here it is again. I'm going to look at it a little bit and realize that the alphas are always on the diagonal, okay, because that's basically the definition of an alpha integral. And the beta integrals are always on the off-diagonal locations. There's no overlap between alpha and beta, so I don't have an alpha plus beta or something like that. It's either alpha or it is beta. Okay, so that means that I can actually write this whole matrix in a way that separates the alphas from the betas. How do you do that? Well, something like this, right? I can split this matrix in 2 matrices. One has the values for alpha. That means I have here a diagonal matrix with 1, 1. Because I multiply alpha with 1, 1, I'm getting alpha, alpha on the diagonal of this small 2 by 2 matrix. Then I can add to it this integral, which only has off-diagonal elements of the value beta. Okay, so if I add these two, the alpha matrix and the beta matrix up, then I'm getting, of course, again, the starting matrix, the matrix I started with. Right, so I just split this matrix into 2 parts. This will help me to actually calculate and diagonalize this matrix. So what I have to do, the procedure that I have to do, that I'm after, is to diagonalize this matrix. I can write this matrix even simpler by saying alpha times the matrix with only 1 on the diagonal. That's this big fat 1 here. That is a matrix that only has 1 on the diagonal. That's called the unit matrix. Okay, so alpha times the unit matrix is really what you see here as the first term in this expression. And then the matrix that is written here right behind beta, I call M. Okay, so M is not a diagonal matrix, clearly, because it has off-diagonal elements. Okay, so the Hamiltonian matrix is written as something that has only diagonal elements with alphas, and something that only has off-diagonal elements, and that matrix I call M. So what I have to do is to diagonalize this Hamiltonian matrix, and what I'm getting then after that procedure is a matrix with only diagonal elements, which I call big fat E. Okay, so that is the matrix that has the answers in terms of the energy on its diagonal. That's what I want. So what I'm going to do is I'm going to write now this Hamiltonian in this new way of writing. Alpha times the unit matrix plus beta times M. Okay, so I get this. Okay, so I have here the column vector matrix, the inverse times the Hamiltonian, which is written now in this new fashion, and then times the column vector matrix again. Okay, so let's do this. I can basically operate this c to the power -1, or the inverse matrix, times the first term, and then times c. Okay, and the same for the second term. So I can just split it out. Right? So the first term is already a diagonal matrix. Okay, that's important to realize. Okay, so if I multiply a diagonal matrix by the inverse of this matrix, and then from the left side, from the right side, I multiply by C. If this matrix is already diagonal, nothing is happening to it. Okay, there's no operation done because it's already diagonal, which means I can just take this this expression alpha times the unit matrix out from this multiplication from the left and the right by C, and C inverse times C equals 1 already. Okay, so that's also a unit matrix. So the end result is I just get nothing. I just get the same that I started from because it's already a diagonal matrix. So every time you are multiplying from the left with the inverse of this column vector matrix and from the right with the column vector matrix, nothing's happening because the matrix is already diagonal. Okay, so that's the first step. But in the second term here, I cannot play the same trick, of course, because M is not a diagonal matrix. That means that what I'm left with is the expression inverse of C times M times the matrix C. That is the operation. That's the operation I need to do, right? So this is the operation I'd like to do numerically. So what I have to do then is to write the matrix M and find the solution to the operation inverse of C times M times C. Okay, that's what I'm trying to do. So I have to diagonalize numerically this matrix. If I find the solution, I find the solution to this problem C inverse times M times C. That's what I want to do. And we can do that numerically. You can do it by hand. This is a pretty simple, 2x2 matrix. So this one actually we could do by hand, and maybe you have learned how to do that in some kind of mathematics class. But that's not the purpose of this course. We don't require people to do that. Even though if you could, please be my guest and have fun with it. But we don't want everybody to spend a lot of time on this, because we can just go to a matrix solver. Okay, so we're going to use that. We're going to use this particular one. There's many online. This is just one of them. This is a nice one, I think. It's good for up to 3x3 matrices. And we're going to just fill out this matrix and try to diagonalize and see what the results are. Hopefully this procedure will make this procedure a little bit more tangible. Okay, so let's go to this. This is the website that it will direct you to. Okay, it's a very simple interface. So what I'm doing here, it says diagonalize. That's the action I'm going to do, diagonalize. Okay, diagonalize a matrix, and I have to fill out the matrix. The matrix that I have is a 2x2. Okay, so that's a 2x2. I could just fill out the numbers. On the diagonal is going to be 0. Off diagonal, first one is going to be 1, 1, 0. Right? That is matrix M. That is the matrix I would like to diagonalize. Okay, just press go, see what happens. And it's going to calculate. And here it is. That's the solution already, pretty fast. Okay, so what it says here, let's look at the answers. The diagonal matrix D has the following eigenvalue. So you see here, I have the answer. That is the solution of the diagonalization of M. The solution is 1 minus 1. And of course, it's a diagonal matrix because that's really what I was trying to do in the first place. Now, the column vector matrix that makes that possible is called P here. Okay, and the values are 1, 1, minus 1, 1. This would be our column vector C. Okay, they call it P here, but that doesn't matter. It's the same thing. Okay, so this would be our column vector matrix. This is the inverse of the column vector matrix. Okay, so indeed, if you take that procedure, what you get here is this expression, this operation will do it. Okay, so what we have done previously is actually put the inverse in front and this column vector matrix on the right. This is the reverse operation, but the answer is going to be the same. Okay, so they define it as P, D, P minus. We defined it as P minus times d times, p. So the procedure is identical in this case. So we have the two solutions now. We have the column vector matrix, P, and we have the diagonal matrix with the eigenvalues 1 and -1. Okay, so remember these values, remember these things, because we're going to import them back into our slides here and see what we can do with it. Okay, so this is what we did. We diagonalized it. This is our Hamiltonian matrix again, just to kind of reiterate a point. We have a diagonal part, which already is diagonal, and then an off-diagonal part that we were trying to diagonalize as well. And we did, okay? So these two terms are written out here once again. You see here in the red box, that is the matrix, unit matrix. I have C minus 1, C. Nothing will happen to this operation, so I can take this C minus 1 out. I can move it to the right, and then C minus 1 times C equals 1 again, which means alpha times the unit matrix. So that's something we already concluded. This is really the important part. That is the green box. That is the operation that we have to carry out, and we just did it. Okay, this is C, the inverse, that's C, and they're called P in the program. All right, and we have now an expression for P. Okay, so we have diagonalized this whole thing. Right, and that should give us E. That's important. So from this matrix diagonalization, we found this solution. Okay, this was called D. This was called D in the program. Right, so we found 1 minus 1. That is what this operation gave us. We also found what C is. C is 1, 1 minus 1, 1. That was called P in the program. Okay. So we have now all the numbers here, all the solutions. So let's basically put this whole thing together and see what it means for us, for our molecular orbitals. So the energy is alpha times the unit matrix. That hasn't changed. But now this operation C minus MC is now written as such. That's D, right? So it's beta times D. So that is what gives me the energies. And there's now two combinations, right? Alpha times 1 plus beta times 1. That's the first solution. And the second solution is alpha times 1, beta times minus 1. Okay, so what I'm getting is this. I get a diagonal matrix with two elements, alpha plus beta, alpha minus beta. And this is something we already know. This is, of course, the exact same solution we found last time. We should, of course. But now we have done this numerically with a matrix solver. Okay, so there's more information because we have also the column vector matrix C. Okay, so this column right here, this column is basically belonging to this solution for E. Okay, so this eigenvalue is associated with this column vector. Okay, so that means this is my first molecular orbital. Okay, psi A, so to speak, has the coefficients Ca, where Ca1 is 1 and Ca2 is also 1. Okay, so from this we can now construct what the molecular orbital wave function looks like. And the same is true, of course, for the other solution, alpha minus beta. That's the second eigenvalue, which is associated with the second column. Okay, so that will be Cb, where the first coefficient is -1 in this case, and 1 for the second coefficient. Okay, so what we can do now, we can write out what the molecular orbital wave functions look like. So let's do that on the next slide here. So the first molecular orbital wave function, this is a general way of writing it, a linear combination of the atomic orbitals 1 and 2. And we have found the column vector that is associated with this wave function. It's A, that's the first column, and it has the coefficients 1, 1. So this coefficient here is 1, and the second coefficient is also 1. Okay, so this is what I'm getting. This is the first solution, the first molecular orbital that I'm finding through this procedure. It's not normalized, okay? So this procedure doesn't do anything with normalization. That doesn't happen automatically. So if we want to normalize it, we can. We can do it after the fact. And in that case, we'll be getting this. 1 over square root of 2. And then between parentheses, I have 1 plus 2. Those are the two atomic wave functions. This is my bonding orbital. Bonding orbital associated with the energy E equals alpha plus beta. What about the second wave function? That will be the anti-bonding. Okay, here it is. This is the column vector that is associated with that solution. -1, 1. And so when I write that, I find this. The second coefficient is 1. The first coefficient, -1, so I can write it as 2 minus 1. This looks a little different from what we've done before, because before we found 1 minus 2. Now, this is kind of the negative of that. Okay, so the question is that a different solution then? The answer is no, it's the same. The negative sign doesn't change, really, the physics. It's arbitrary. It's arbitrary which of these two actually carries a negative sign, because the exact same physical properties are carried by both solutions. So either one is fine. Okay, so within this particular matrix solver, this is the way it is written, where -1 is associated with the first atomic wave function, the positive with the second, and we find this solution. So it's the inverse or the negative of the solution we found before, but physically these two solutions are identical. Okay, so here is this is what happens after normalizing that function. 2 minus 1 is a perfect solution here, as would be the negative. If I multiply this whole thing by a -1, I would have the same solution, in fact. Okay, in terms of amplitude, the negative does not matter too much, but does matter if I take the modulus square of this thing, I should be getting the exact same probability, and that's still the case, okay, because the negative sign squares out. Okay, so this is basically what I'm finding from this procedure. Remember, we found two things. This is the beauty of this matrix diagonalization procedure. I find the energies and I find the column vectors, which means I find expressions for what the molecular orbitals are. There's no mystery here. You got all the information you need. Here's the same molecular orbital diagram once again. It looks the same as before, but now I'm just explicitly writing the form of the molecular orbital wave functions, psi A and psi B. Okay, the plus combination and the negative combination, where one is subtracted from another. Again, it doesn't matter if you have 1 minus 2 or 2 minus 1, because the naming of these two atomic orbitals is arbitrary. If I flip the molecule around, it's still the same molecule, you would basically flip these signs around as well. Okay, so the naming of these two carbon atoms is arbitrary. This could be 2, and this could be 1. It's still the same molecule, right? Physically, nothing changes. So the negative sign doesn't change the physics of the problem. Okay. Now, let's make this a little bit more complicated, because a 2x2 matrix is the simplest possible case, okay? But of course, there are more complicated scenarios. So let's look at butadiene, which is also a molecule we looked at basically during Wednesday's lecture. The procedure is kind of the same, okay? So what we're going to do now is we're going to find the explicit expressions for the molecular orbital wave function. So psi A is the first solution. It's a linear combination of all the 4 carbon p orbitals. There are 4 in total, so I have to make a linear combination of 4. But there are 3 more solutions, of course, that I can call psi B, C, and D, which look the same, but the coefficients have different values. Okay, and together they form this set of molecular orbitals. Last time we looked at what they look like after diagonalizing the Hamiltonian matrix, but we didn't show explicitly how that was done. So let's do it again, and now just pay a little bit more attention to the steps involved in diagonalizing this matrix. Okay, so here's the matrix once again within the Huckel approximation. We are applying the Huckel approximation because, of course, the problem is more complicated than we make it seem to be. The alphas here are on the diagonal, the betas are off diagonal, and the next one over is going to be 0. All the other elements are going to be 0. Only the diagonal and the adjacent elements next to the diagonal are going to be non-zero. This is the Huckel approximation for butadiene. So we can write this thing out in exactly the same way as we did for the 2x2 matrix. Of course, it's going to be a little bit more work because now we have a 4x4. But as you can see, it's exactly the same recipe. Nothing has changed. Okay, I can split it out in alpha times the unit matrix. The unit matrix, of course, now has 4 values on a diagonal. It's a 4x4 matrix. And beta, the same story. Beta has a lot of zeros on the diagonals, and then only the non-zero elements are the elements adjacent to the diagonal, okay, on both ends. And they have the value 1, as you can see. So what we have to do is we can write Hamiltonian again in this form. Alpha times the unit matrix plus beta times M. M is this matrix here. Okay, and our task then is to solve or diagonalize the matrix M once again. Okay, so what we have to do is this procedure, the same procedure, nothing has changed, but now the matrix is going to be a little bit bigger. That's all. So what we have to do then, we have to go to our matrix solver, fill out the matrix, press go, and then see what the solutions are. Okay, that's what we have to do. It turns out this little program that I showed you is good for 3x3. It's not so good for 4x4, but there are many other programs online. So if you do that, then you'll find the solution to this procedure. Okay, and I just did it this morning, and this is what I'm finding. Okay, so this operation, diagonalize the matrix M, gives me the solution, which is called D. Okay, so the diagonalized matrix I call D, and this is what that looks like. Okay, so this is really, I fill out the matrix M, I press go, and then the program spits out D. This is what it says it looks like. All right, here they are. Indeed, it's a diagonal matrix. It has non-zero diagonal elements, and all the other elements are 0 here. So these are related to the energies. So let's extract the energies from this solution here. We have to remind ourselves that these are not the energies per se, because the energies are found in this way, right? Alpha times 1, the unit matrix, plus beta times D. So what I'm getting, if you do that, you get 4 solutions. You get alpha, and I'm going to just write out these terms, okay? There's 4 different terms. So, and they're not necessarily in order. Some people think that if you do this and you go to a matrix solver, that it should arrange all the eigenvalues in terms of highest to lowest values, but that's of course not the case. So we have to be smart about it. This value here is the highest number. If you type this into your calculator, you find 1.62 times beta, because the beta is right here, and then plus 1 times alpha. So I got alpha plus 1.62 beta. That's the energy that is having the highest eigenvalue. Since beta is negative and alpha is negative 2, that's going to be my most negative energy. That means it's going to be my most bonding energy, right? So the next energy is alpha plus 0.62. And again, these things are a little bit out of order. I believe this is the next one. Okay, so this is 0.62, if I'm not mistaken. Yeah, I think so, yeah. Okay, the next one is going to be 0.6 minus alpha minus alpha minus 0.62 beta. That's the next one. And then the last one is alpha minus 1.62 beta. Okay, so that is the most negative solution that we find here. So these are the energies, and they follow directly from this recipe. Okay, so we have done exactly the same step as we did for the ethene molecule. We do it now for the butadiene molecule. The only difference is, of course, that this matrix is a little bigger. And of course, we have to realize that the ordering of the eigenvalues here is not necessarily from high to low. They are pretty much randomly distributed. So you have to know which column you associate with what energy. Okay. So these are the energies. Let's look at the, the actual wave functions, because the wave functions depend on the values of this column vector matrix. All right, so we have 4 columns now, and these correspond to the coefficients for each of the molecular orbitals. So let's look at that. Let's start to find it. We have to be smart about it, because we have to find which psi corresponds to which column. Okay, the energy that I found on a previous slide, this second column had the highest eigenvalue, which means the most negative energy, and that would be psi A. So psi A, the most bonding orbital, is associated with this second column here. Again, nothing in this procedure guarantees that these things are ordered, so you have to be fishing out the right wave function associated with the right energy. But if you do that, then you see that, okay, I can have the coefficients here. So the first one, value 1, that means C here is 1, so I just get the atomic wave function of the first carbon atom. Then I get 2 times, this is basically the second coefficient, the third coefficient, they are the same, okay? And then the last one here also has the value 1. So this is my first solution, and this is associated with this energy, EA, alpha plus 1.62 beta. This is what we got from the previous slide. Hasn't changed. Right? So this is my first solution. Now, if you look at this, let's analyze this a little bit. What does it mean? 1, 2, 3, 4. They all have positive coefficients. Okay? They all have positive coefficients. 1 plus square root of 5 divided by 2 is a positive number, of course. And that means there is no sign flipping here anywhere, which means relative to one another, these wave functions, these atomic wave functions, all have the same sign, aka the same phase. There is no node. This is a wave function, and a molecular orbital wave function that does not have a node. Okay, and we know, of course, that if you don't have a node, that your energy is going to be very low. Okay, because adding a node increases the energy of the wave function. Okay, let's go to the second wave function. That is this guy here, this column. This was the second lowest energy that was associated with the last column on the previous slide. So this is also the column that we have to look at for finding the next wave function here, psi B. So let's just fill it out. There's a negative sign here, as you can see, negative. This value here, the value right there. This value right here, the value in front of the atomic wave function 3. And the last one has coefficient 1, so that is not changing the situation here very much. So what do we see here? Let's analyze it once again. This is a negative sign. So here, the wave function has a negative sign. So the phase of this wave function is flipped relative to what it is in A, okay? Because there it was positive. The second wave function also has a negative sign. How do I know that? Because 1 minus square root of 5 is going to be a negative number, okay? So both of these coefficients are negative numbers. The third one is actually a positive number, okay? 1 minus square root of 5 times minus 1 actually is a positive number. So this coefficient, coefficient 3, is positive, and of course, positive 1 is also positive. So the last two are positive, the first two are negative, which means it's going to be one nodal plane. Right? The nodal plane will be situated in between 2 and 3. because that is where the sign is flipping. And you will see that, of course, on the next slide, where I show what these orbitals look like. That's exactly where the nodal plane sits. It sits in between wave function 2 and 3 of the atomic wave functions. The energy associated with this state is what we found on the last slide, is alpha plus 2.62 beta. Okay, and that was found in the fourth column on the last slide. That was the energy that I write out here as such. Okay, the next one that is found in the third column, that is psi c. So let's take those coefficients and write out the entire thing. Here it is. Oops, did I make a mistake there? Yes, there should be a negative sign right there. Apologies for that. Okay. Oh man, I did the wrong thing here. Ah, boo. It looks exactly the same as, okay, let's correct that. That is not good news. There should be a negative sign right there. I don't know what happened there. Apologies, folks. This one is correct. There should be a negative sign in front of this guy as well. Okay, so this should be negative. That's it. Okay, so what do we see? We see negative. This is positive, so there's a node between 1 and 2. Okay, and this is going to be negative, and this is going to be positive. So there's another node right here. Okay, so that is what we see for the option C. This is the energy associated with it. And then the last one here is D. Oh, I flipped. Oh man, I made a big fat mess here. Okay, apologies for this, folks. I did it this morning very quick, just before the lecture, and there's a couple of negative signs and positive signs that I mixed up. Okay. In any case, this, if I do it correctly here, this should be a positive sign. This is a positive sign. If I believe this first column right here, okay, the energy associated with this one should be alpha minus 1.26 beta. And if everything is right, this wave function should have 3 nodes, so 3 times a phase flip. But the way it's written right now here, unfortunately, I did a bad job copying the columns here over here. So apologies. I will correct it, of course, but that doesn't really help you at this point. So let's relate this to the final picture, which is exactly the same picture as we showed last time. That was on Wednesday. And what we found is this. The first psi A is this one here, and it has no nodes, and therefore the lowest energy. Second one is B. The node is in between here, as we kind of verified on the last slide. Between atom 2 and 3, there was a flippage of the phase, and that's exactly what you see here. That leads to a higher energy relative to the previous orbital. C has a sign flip here between 1 and 2 and 3 and 4, total of 2 nodal planes, therefore higher energy. And the last one flips everywhere, okay, and has therefore the highest possible energy. So that is really what this story tells us. Okay, so the bottom line is this procedure, this matrix diagonalization procedure, gives us the energies, and it also gives us what these molecular orbitals actually look like. Okay, and that follows from the coefficients. And hopefully this explanation, even though I messed up the the last coefficients a little bit there, I will correct it, folks, I promise. But that is basically how it works. Okay, so that's how you can find the shapes of these wave functions. Okay. Yes. Okay, so this is it, folks. I think this is a good place to stop. So this is the last new piece of information that I had, and we'll just conclude. This is it for the course, and next week we'll be doing rehearsing. Okay, we're going to practice stuff. So let me know if you have any questions for me at this point about this particular lecture. If you have questions about, what's going to happen next week, or questions about the material, be welcome in my office hours, which will happen at 1 o'clock today. So the virtual door is open. I don't have a lot to say about midterm 2 explicitly. I have been in conversation with several of you about your midterm. Some people have questions. Feel free to ask questions to me or the TAs about the midterm. The average was 51%. Okay, so that was the average. It was higher than the first. You know, it's still a little low, I think, but you know, that's just what it is. I think you know, this quarter was very difficult for most people again because of the remote learning. Typically, in the live version of this class, people seem to be doing a little better because I think there's more interaction, more people show up for office hours, and you know, we can really address problems. If you do everything on your own, I think it's going to be just complicated. So that's why I want to spend the entire week next week on practicing problems, looking at problems, and really talking about them, solving them, but also trying to understand what these problems mean. Okay, so we need to understand both aspects, of course, right? So yeah. So Michael has a question. He's trying to do the 4x4 in the program I just showed you, but the program doesn't do it. It does do it up to 3x3. Why do I show you that program then? Because it turns out next week we have one more assignment due. The homework is due on a Friday, next week, Friday. But it's supposed to be a fun homework. We're going to use the same program I showed you in this lecture, and you have to solve a 3x3 matrix, and that's what the program can handle perfectly. And you have to do exactly the same steps that I showed you here on these slides. Okay, so that is what you have to do next week. That's the only assignment left. Everything else is going to be practice. All right? Okay, folks, thanks a lot.